There's a famous quote from Richard Feynman about the Schrodinger equation, where he claims that it's not possible to derive it from anything you know, and that it came out of the mind of Schrodinger. If you were a young physics student, as I was and still am, you may have been put off by this quote. Is the foundational equation of quantum mechanics just a random guess? In a sense, yes, but there's more to it than what Feynman lets on here. Schrodinger did essentially guess his famous equation, but there was genuine reasoning behind it. It was constructed through a logical analogy to another realm of physics. In this video, I will present an abridged version of Schrodinger's original derivation of the time-independent Schrodinger equation. In the early 20th century, it was discovered that classical mechanics, based on the work of Isaac Newton, was in conflict to observations of the microscopic world. Basic atoms, like the hydrogen atom, could not be explained through classical mechanics. The nature of what light actually was had been a debate for many years. Newton thought that light was a particle, while Maxwell's equations eventually described light as an electromagnetic wave. When physicist Max Planck studied the emission of radiation from heated objects, he found that classical electromagnetism failed to explain the observed spectrum of blackbody radiation. In order to overcome this issue, he postulated that the energy of blackbody radiation was discrete in little packets of energy, for which Einstein later reinterpreted to say that light as a whole came in discrete packets of energy called photons. This energy of a photon, given by the Planck-Einstein relation, is equal to Planck's constant h times the frequency of the photon. We then have the equation E equals hf, where f is the frequency of the photon. This can be rewritten in terms of the angular frequency 2 pi f if we define a new constant h bar is equal to h divided by 2 pi. Therefore the energy E equals h bar omega, where omega is the angular frequency. This equation can be rearranged algebraically to show the angular frequency omega of the photon equals E divided by h bar. Later on, Louis de Broglie extended the Planck-Einstein relation to ordinary matter previously thought to be particles, such as the electron. Not only does light have dual properties of both wave and particle, but so does ordinary matter. The next question would be then, can we find an equation that we can use to solve for the matter wave itself? And this is where Erwin Schrödinger comes in. Schrödinger was trying to find a wave equation that could describe those matter waves, but it was very difficult to find this equation from the ground up, so Schrödinger looked back to the physics of light in the field of optics. In wave optics, light is described as an electromagnetic wave, such as in Maxwell's equations. Ray optics describes light as a ray, a single straight line passing through space. It can be regarded as the path of a particle of light. A ray is a line perpendicular to the wave fronts of light in wave optics. Therefore, ray optics is derived from wave optics. We can then directly compare wave optics and ray optics to classical mechanics and wave mechanics, or as it's known today, quantum mechanics. The question is then, can we find a formulation of classical mechanics where the motion of a particle is related to a wave? Thankfully, the answer is yes. The equation we're looking for is the Hamilton-Jacobi equation, which includes a quantity called the action. The action, denoted as S, is derived from Lagrangian mechanics, an alternative formulation of classical mechanics. The action S is equal to the integral of the Lagrangian over time from some start time to end time. The Lagrangian itself is equal to the kinetic energy of the particle minus the potential energy, p squared on 2m minus v, where p is the total momentum of the particle in 3D space, m is the mass of the particle, and v is the potential energy. The Hamilton-Jacobi equation states that the partial derivative of s with respect to time equals minus the total energy of the particle. If you integrate this equation over time, you'll find that s is equal to minus the energy times t plus some constant. Since you integrated a partial derivative with respect to time of the function s, then the integration constant here is a function of space alone, the coordinates xyz, which we will write as w of xyz. Therefore s equals w of xyz minus et. Now we can look at the supposed wave properties of s, the action. Consider at some time t0 that s is equal to some constant c. Then s of xyz in t0 equals c, which equals w of xyz minus e t0. Rearranging algebraically, we find that w of xyz equals c plus e t0. w of xyz is a surface in space coinciding with s equals c. Reapplying this for a time t equals t0 plus dt, we find that s of xyz t0 plus dt equals w of xyz minus e times t0 plus dt equals c. Rearranging algebraically again, we find that w of xyz equals c plus et0 plus edt. During the time interval dt, looking at this we can see the surface s equals c has moved. This is exactly the way wavefronts move in optics. From this we can see that s can be loosely considered as a wavefront. Now that we've used the action to find a wavefront evolving in time, we want to find its velocity. We can consider a normal vector of magnitude dn to the surface w of xyz at time t0 that represents the distance to the surface w prime of xyz at time t0 plus dt. The velocity of this normal vector is the velocity of the wavefront and is written as dn on dt. But how can we find this velocity? Well, we can use some basic properties of the surface w we are investigating. The change in the surface w from time t0 to t0 plus dt can be found by subtracting w from w prime and can be written as a differential dw. This differential dw equals e dt. However, the differential dw can also be calculated using the rules of multivariable calculus as the sum over the derivatives of the spatial coordinates times each corresponding spatial coordinate, aka dw on dx times dx plus dw on dy times dy plus dw on dz times dz. But this is just the same thing as the dot product of the gradient of w with the vector dr, which can be expanded as dw on dx times x hat plus dw on dy times y hat plus dw on dz times z hat, dotted with dx times x hat plus dy times y hat plus dz times z hat. The dot product of the gradient of w in dr can also be calculated by the magnitude of the gradient of w times the magnitude of the vector multiplied by the cosine of the angle between them. However, the surface w is what's known as a level surface. That is, a function w of xyz in 3D space that just equals a constant. I won't go through the proof here, but it turns out that the gradient of any level surface is orthogonal to it, meaning that it points in the normal direction to the surface. But since the vector dr here represents a change in the spatial coordinates from the surface w to w prime, then dr just equals the vector dn that we had on the slide before, meaning that it also points in the normal direction to the surface. So the gradient of w and dr actually both point in the same direction, and the magnitude of dr is just dn, the distance between the surfaces. So the dot product here can be rewritten as just the magnitude of the gradient of w times the distance dn between the surfaces. Equating this with e dt, you find that the normal velocity dn on dt just equals the energy divided by the gradient of w. But in order for our answer to actually be useful, we need to know what the magnitude of the gradient of w actually is. To find it, we first note that the total derivative of the action with respect to time is just the Lagrangian, which follows from the fact that the action is just the integral over time of the Lagrangian. Using the laws of total derivatives, this can be expanded as a partial derivative of s with respect to t, which is just minus e, which we know from the Hamilton-Jacobi equation, plus the sum over the spatial derivatives of s times the corresponding velocities. We can add e to both sides and use the fact that L equals t minus v and e equals t plus v, where t equals the kinetic energy, to find that 2t equals p squared on m, where p is the total momentum of the particle. The right-hand side of the equation is just the sum over the spatial derivatives times the velocities from before, except rewritten using summation notation for convenience. For example, x1 would equal x, x2 would equal y, etc. Rearranging algebraically and noting the fact that the total momentum squared just equals the sum of the component of the momentum in each spatial direction squared, we see that the partial derivative of s with respect to any spatial coordinate xi just equals the component of momentum in that spatial direction. Taking the gradient of w using this fact, we find that it equals the sum of each momentum component times the corresponding unit vector. To find the magnitude of the gradient of w, we will form a dot product with itself to find its magnitude squared, then take the square root. The dot product of the gradient of w with itself is p squared, so the magnitude of the gradient of w is just p, the total momentum of the particle. Now we've found that the velocity of the wavefront equals the energy of the particle divided by its total momentum. You can rearrange the equation E equals p squared on 2m plus v to find that p equals the square root of 2m times e minus v. This gives our final result for the velocity of the wavefront as e divided by the square root of 2m times e minus v. Since we now know the velocity of the wave, we want to actually do something with it. The simplest way to go about it is to plug it into some sort of known wave equation. Well, there is a well-known differential equation called the wave equation, which is used in many places in physics. It's used for light, or for the wave created by a plucked string on a guitar, a lot of things. It's the simplest sort of differential equation we could plug the velocity we found into. The wave equation is just the Laplacian acting on the wave psi minus 1 on the velocity v squared times the second partial derivative of psi with respect to t, which altogether equals 0. If you don't already know, the Laplacian of psi is just the sum over the second spatial derivatives of psi. Plugging in our equation for v, we find that the wave equation becomes the Laplacian psi minus 2m e minus v on e squared times d2 psi on dt squared, which all equals 0. As it is right now, this equation looks a little odd, but since we want to find the time-independent Schrodinger equation, we assume that the wave psi oscillates at a constant rate over time. Since psi oscillates at a constant rate over time, we can plug in the expression of the angular frequency from the Planck-Einstein relation earlier in this video. If psi is some sort of exponential or sine or cosine function with a constant angular frequency omega, then we can rewrite d2 psi on dt squared as negative omega squared psi, which equals negative e squared on h bar squared psi. Plugging this expression for the time derivative into the wave equation results in Laplacian psi plus 2m e minus v on e squared times e squared on h bar squared psi. Cancelling out the e squared terms results in Laplacian psi plus 2m e minus v on h bar squared psi, which all equals 0. Subtracting the second term from both sides, then multiplying everything by negative h bar squared on 2m and expanding all brackets gives the full time-independent Schrodinger equation. Thank you for watching this video. This is one of my first attempts at making videos, so I hope it was relatively clear. If you have any questions, please post them in the comment section, and I'll try to answer them as best I can.